Welcome to the next session. One reminder, as you're leaving the session, you can scan your badge at these pods that are at the doors in order to be able to provide us with some evaluation on the way out on Jason's presentation. So at that point, I will let Jason Raber give his presentation on virtual Deobfuscator.
Okay, so yes, as he said, my name is Jason Raber with Hex Effect, and today I want to go over an automation technique to remove virtual obfuscations from malware. So here's a quick overview. What the heck is this type of software protection? Why we even care? What is kind of the state of the art? What's been done? My solution? Some potential future work with this product, and where to get the source code and any questions you have. So what is virtualization obfuscation? It's a type of software protection focused mainly on anti-reverse engineering. So there's lots of different protections out there, from encryption to anti-debugging to anti-tamper, but this one's focused just on anti-reverse engineering. And how it basically works is the virtual machine will create the bytecode from the original code, okay? And then with the current technologies out there, they'll actually randomize it. So each time there's a protection, it's a different virtual machine. So the opcode or the bytecode that's generated from the original code is going to change each time. So as you see, a lot of times they'll even pick a RISC type architecture. So I've looked at this in the past when working with the Air Force or working with some defense contractors and looking at malware and finding these types of protections. And one thing that is, if you play around with the protection, is the original binary is lost at that point. So like, if you're dealing with encryption or something along those lines and you have a stealthy way to probe memory and dump the memory, you can reverse engineer out the original binary into the semi-C code or whatever it was originally. But with this one, it's a lot tougher. Okay, so again, why do we care? Is because in looking at it, it's a really tough one. I mean, really tough. So if you do like from a static analysis perspective only, when you disassemble it, of course, if you got bytecode, the disassembler doesn't understand that bytecode, right? Especially if it's randomized each and every time. So it's hard to find that bytecode, and you have to spend RE time to go find it. Then from there, if you want to take the dynamic and static, you can start looking at the run trace from it. Problem with that is you got a vast number of instructions, and it's hard to figure out where the virtual machine is versus the actual interpretation of those bytecode. In a case in point, on this project, one of the programs that I used was Themita, and I took one instruction and I turned up the VM completely with all its bells and whistles. And it went and generated a run trace for that one instruction of around 3 gig. So that's pretty hard to go through 3 gig and try to figure out what it's doing, right? So how I've done it in the past is essentially slogged, which that means start reverse engineering it, pull up dynamic, static, find the bytecode. Once you find the bytecode, start reversing the VM so that you can create your own little disassembler, which is fairly fast, but still, it could take a while depending on how complex the VM is itself and how complex the bytecode is. And then what I found out, a long time ago when I was looking at this stuff, is that the disassembler that I created and the work that I put into creating it and breaking at one particular protection, I was given another protection and it wasn't the same, and that's what I come back to, where it's jittered each and every time. So break once, break everywhere doesn't work. So I started thinking about, some sort of an automation technique would be nice. Okay, so here's some of the state-of-the-art work that's been done out there. I could spend an hour on each one of these. So I put it on this slide just to give you some reference. You can go check it out and read up on it if you're really interested. And they've had some pretty good success. But what I was trying to come up with was a solution that, I keep getting the wrong thing. It would have more automation and be complete. So I came up with this virtual Deobfuscator. And what it does is it uses a run trace from a debugger, obviously, and filters out the virtual machine interpretation, okay? And what you're left with is the semantics and syntax of the original bytecode as it's been translated and executed. And I also wanted to be architecture agnostic, so it doesn't matter how many jittering of the virtual machine there is, it'll still work on all the different products too that are out there. And of course the way it works is through recursive clustering, and I came up with a people optimization. I'll talk more about that as we come to it. So here's kind of a flow of how it works, right? So again, create the parse, create the run trace, then feed it into the virtual deobfuscator. It'll create it'll parse it and create a little database. It'll start clustering. It'll recursively cluster until it cannot find any more. Okay. Then the idea is you assemble it, which is part of the repackaging of the binary, and then I'm going to run a little people optimization. The reason I say people optimization is I used to write compilers for Texas Instruments way back when, and in the code generator, sometimes in the compiler you have to punt on certain things you just don't understand. So at the last phase of the code generator is a people optimizer in case you end up with instructions like move 0 EAX or something like that and then repeated. And it's like, why would the compiler do that? Well, that's a whole nother talk, but we have a people optimization to go through. And my theory was taking a CISC architecture and converting it over to a RISC architecture, there's going to be some instructions that the RISC doesn't have a one-to-one, so it's going to generate some bloat. And so that was the whole idea between that, or for that. So talking about the parser, I picked a couple common ones out there, Ollie 1 and 2, Immunity and WinDebug. The idea is, you know, when it parses it in, it creates an XML parser or XML database. And for Python, there's a nice little XML parser, so I can use and reference, pull out instructions, or as you're looking at run traces, you're looking at register effects and what the results are, those types of things. And then the other idea is, you know, with the source code being available, if you have your own custom hypervisor, hardware emulator, once upon a time I had one when I was in the Air Force, and they're pretty useful, but they're pretty expensive, so you can customize it. This slide again, you know what XML looks like. Here's kind of the format. The point that I want to talk about is when I was developing this project, I really wanted a way of testing. So I created this flag called -t for verify, and what that means is after I've parsed it in as an XML file, you can run this -t, and what it does is it reverses it. So then you'll recreate the run trace, and then the recreated run trace is going to be verify txt, and you can diff it with your original. So if you're adding your own debugger to this thing and you want to test it, that's one way of doing it. And you'll see where I talk about backtracing, I also, it's again more testing and ways of verifying you're not screwing anything up. It saved me a lot of time. Oops. Hang on a sec. So the clustering, this is kind of the high-level conceptual idea that I was coming up with when I proposed this project was, so over on the far left-hand side, you see before the past one, that's your run trace, okay? So you got all these instructions. So I come up with a unique way, and I'll come to that in another slide about how I identify what a cluster is, okay? And from there, the idea is, like say the first pass, I create these clusters that are based on very small snippets of assembly code. And if I see those same snippets of assembly code repeated, I name them the same one. So in this case, think of, you see cluster B where it's got the move and the compare and the call. Everywhere that those exact same instructions come up again in the run trace, I label it as B. And of course you see A. So then when we go to the next phase or the next pass of the clustering, I start taking those A and B and find if there's any other A and Bs. So if in Python, basically I create a hash table, and from that hash table I just look and see if it's being duplicated. You know, so if I look at the key of AB and say it was AB being repeated anywhere else, if it is, I have a cluster. So I'll create AB, AB. The idea is, as you can see on the fourth pass, is that the large clusters are going to be my virtual machine. Okay, and so I can just weed those out and get rid of them and not pay any attention. And what's left is D and E, which is what I believe is going to be the translated bytecode. And then that's the part that I want to reverse engineer and I'm interested in, right? Okay, and I already kind of walked you through clustering. Okay, so again, if you pull down the source code and you start playing with this guy, here's the nomenclature. There might be a better way of doing it, but this is what made sense to me at the time. I use the alphabet to represent the round of clustering. So in this case, I'm on the third round, that's C. 2 is just a unique identifier, so you're going to have C, 1, 2, 3, 4, 5, all the way up until we run out. We're going to run out of numbers, but. So then the depth is, it's a visual clue as to when you look at the final results. What I wanted to do was show not depth is in rounds, but more in depth in how many how many instructions are under one cluster. And that'll make more sense when I showed you like code virtualizer or VM protect. And 8 represents how many instructions make up this particular cluster, right? So we're on round 3. This is the second cluster in round 3, and it has 8 instructions in that cluster. Okay, so as part of the project, I said, well, before I run off and start looking at VM Protect or any malware or anything along those lines that has these types of protections, I created a very simple test case to verify and test the whole clustering idea. So it's two loops, 2 nested loops, and as you can see from the logic that this instruction is only going to execute once, the move EAX dead beef, right? This slide, you know, I put it on here, I got a lot of notes underneath it. So I'm going to put this presentation up on GitHub. You can download it with the source code. Read those notes and you'll kind of understand. Again, it's a diagnostic for me. There's a lot of this that will fly across the screen. For each round of clustering, you're going to see all this type of stuff. But it's easy to track what files are being generated. If something happens wrong or you're debugging your code, this could save you. So the end result of that little short example, you can see, you know, we only got down to F. As far as clustering rounds go. And you can see F jumps out at you as it's got 47 instructions, and it's being repeated, you can see down a little bit below, again, and with the larger ones that we're looking at, real protections, there's going to be a ton of them, right? But again, this is not protected, this is just a loop. But really what I wanted to see was, would the clustering, would it pull out the move EAX dead beef as a unique instruction? And it did. So then that said, well, okay, it's time for something a little more interesting. So what I did was I wrote about 30 or 40 different assembly instructions. Here's one of them called OR AX C0 A1. The idea is whatever's in the AX, when it does this operation, it'll become dead. It's easy to debug. So when I ran it through the code virtualizer, I can't even remember how many instructions it generated. But you can see that it clustered K7 and K8. And in that cluster, there's 3,508 instructions, and then the other one is 3,196. This was kind of the theory that I had that this would actually work, right? So the virtual machine would be detectable, and we'd be able to weed it out, and what would be left is what we're interested in. And so when I did a little REing, there's a little bit of code obfuscation here, but you can see at 49D064, I have no mouse, that's cool. You'll see that there's an equivalent OR instruction, and if you debug it, you will see that what's on the stack becomes dead. Okay, so I wanted to take a little bit of a deeper dive. It's, I think, fairly simple, understanding how the clustering works and stuff, but so the idea is the very first, and I had to kind of figure out my window size, and honestly, when I started this project, when I wrote the proposal, I said, I have no idea how I'm going to cluster exactly. But as I dive into it, I'll figure it out, and that's exactly what happened. So when I created a hash table on all the virtual addresses, okay? So what's worth explaining here is, do you see where it says 413D5, D8, DB? All right, well, look at those line numbers. What that means is that line number is the line number it is in the run trace. So 44, 77, 115, 148. Again, that's where it's that exact instruction's being executed in the run trace. Of course, D8 and DB follow that, right? But what's interesting is look at DE. It also has sequential numbers, except it starts with a 14. So I thought, I wonder if that's a basic block, right? A change in a basic block. And when I disassembled it, you can see that DE is a new basic block. So I said, well, my first pass on this guy, I'm going to create this, part of my algorithm is compressing basic blocks from the run trace, okay? So that same example we see up above, okay, you see how it's got 3 instructions and they're all sequential and they're the same length. All right, so then what I do is I say, well, that's a cluster. That's the very first cluster in this example, right? So A16_pound3 is saying that, you know, for round 1A, right, this is the 16th cluster, because this is actually a real example, so I just copied and pasted. And it has 3 instructions in it, right? So that's the very first pass, is this compressing of basic blocks to get it faster, right? And so then once I'm done with compressing basic blocks, I move into the second phase of the clustering, which is the recursion, where I just do this greedy clustering. It's really pretty simple, actually, because I create another frequency graph from the next round of clustering, right? So I can see A1 pound 2, A2 pound 3. Okay, I look in my hash table and I say, well, is that ever being repeated? And in this case it is, right? Directly underneath it. So I say I got a new cluster, which is round 2, which is B1, and then pound 5. Pound 5 being there's 2 instructions and 3 instructions. Simple addition. Now I've got my 5 instructions underneath, right? So, and this just kind of repeats until, again, it can't find any more. Now, this step here, you can comment this code out if you wanted to make it really fast. But I did it because, again, what I was talking about, verification. This has saved my butt a number of times when looking at it. If I wrote some code that was bad and I'm trying to troubleshoot it, sometimes debugging Python code or running through a gig run trace is not easy, just pinpointing where I made a logic mistake. So what I do is I do this backtracing, which I reverse the process. So whatever round I'm in, if I'm deep in like 4 or 5 or 6 rounds, I start decompressing it and putting it back, as in, you can see right here, if we were doing 2 rounds, if you were to look at the files that are generated, it's actually like B_backtrace, A_backtrace.txt. You look at them, you see A55 pound 2 is made up of 2 instructions at these 2 virtual addresses, right? So if you go to B up above, you'll see it's made up of clusters, right? So at the very end, when it's all done, it creates a new file called final backtrace. And that final backtrace is the cluster. So remember that big long cluster I said, K7, and it had 3,000 instructions in it? It will actually decompose it so it has all the virtual addresses. And from there, I'll generate a final backtrace that will be the recreated run trace. And I can diff the 2 and say, did I make a mistake? If they match, then my logic was correct. If they don't match, then it's easy for me to find out where it went off into the weeds. And so one of the last steps is creating the new cluster. That's kind of obvious. And then the very, very last step is I create a file called final_assembly.txt. That's the file as a reverse engineer you want to analyze, okay? So when I showed you that example of code virtualizer, right? That's the file you're looking at, and you're looking at these big clusters. So back to our very simple example, you see the move EAX deadbeat standing out, and that's the area that you're interested in, right? If you want to not look at assembly code for whatever reason, then you can also just look at the last round, and the last round's not going to have that, but you'll see the virtual address, and it'll stand out, and it'll become obvious. If anybody is a VI editor, a guy like myself, then I put in some extra help. That's what this more on formatting is. So in some of the examples above, I didn't put it in because I didn't want to clutter up the presentation, but it's worth noting that you see K2, this is again a real example. K2, it's got 3,000 whatever. It's on line 15 and 990. So in that final assembly.txt file you're looking at, so if you just want to go to that line real quick, you can do that. And then the next number is the 15, which tells me what my offset is currently. Of course, you can in Vim look down and see what line you're currently on. And then the 5,807, if you want to find out where that cluster begins in your run trace, you can bring up your original run trace, go to that line, and that's where it begins. And then, of course, you can copy the 3,226 from there, and then you have it. But I actually make that a little bit easier because I created chunking. So when you're running it through, at the very last, when it's done and created the final.txt file, it creates a directory called chunk cluster. And what it does, it takes all those clusters and puts these files in there. So the big long clusters. And look at this example here. You see F34 compound 173, right? So those 173 instructions, I might be interested in not going and finding the offset and the run trace and figuring out where it is and copy and paste it if I want to assemble it or something along those lines. So if I just want to do a static or any kind of a static analysis, I can just go to that file and see it. The underscore 19, that's just the file offset in your final assembly.txt that you're looking at. What I wanted to also point out is I put ASM just because I get color syntaxing and I like that, but you can't really assemble it. Why? Because if, you know, Ollie debug puts offset, or it uses things in its instructions that the assembler doesn't like. So then what I wanted to do eventually, or I want to get to the repackaging phase, which means I want to assemble the final results, right? But I want to remove the virtual machine and just assemble what's the good stuff, right? So I can start reverse engineering. So then what I did was I created a new flag called -s. The concept behind that is look at this real example. You say K2 and K3. Clearly that's the virtual machine at work, right? Because it's huge, it's a cluster, it found it, it's repeated on multiple lines. But all that from E32 to E64, all that cheddar is what you're interested in, right? So I create another file. If you do -s and put some sort of size limit, what you're saying is any clusters that fit within a certain range of this offset or this size, put it in one file. So look at K2, we're at 3,265. If I put 1,300, anything that's less than or at 1,300, it's going to start creating a new file. And it does that until it hits something that's larger than 1,300. Does that make sense? So E32 and E64 and all those clusters in between get put into a file called 23.asm. And that file is all the instructions within that range, just to make it easier, right? Because eventually I want to assemble that. But as I started to assemble that, as I said before, it didn't really work. And I got another slide to describe how I got that to work. So at this point, I'm using Themeda, Code Virtualizer, VM Protect. I'm looking at all of them, and the results are great, but it's like, well, I want something a little more juicy than some handcrafted assembly code. So I used a program I found called a blood alcohol calculator that tells you how many drinks you need to have before you're legally drunk. So that was 77 instructions. When I ran it through VM Protect and Code Virtualizer, it was around 255,000 instructions. That was the bloat. When I ran Virtual Deobfuscator on it, I was left with 40,000 instructions. Pretty sweet, right? 85% reduction. But as I'm looking at it, I'm like, well, I really wanted it to be 77 or something similar, right? Maybe 100, 120. What the heck is 40,000? That's a lot of work, right? So when I started looking at it, I realized that they interleaved code obfuscation in with the virtual obfuscation. So it's a nested protection. And then my people optimizer, and I was thankful that I was fast on this project and was able to meet my milestones early, because now instead of writing a simple people optimizer, I had to write a code obfuscation, deobfuscation type utility, right? So, you know, here's a couple little small examples, but believe me, there was, I don't know, literally 100, I'd say 100 different ones. What was interesting though is looking at the three different products, they were using a lot of the same things. Of course with x86, I mean, how many kind of random code obfuscations can you really come up with? And these are again very simple, ridiculous, easy things to do. So, okay, so back to repackaging, I use NASM. I looked at MASM 32, but just to assemble a no-op, you had to include stuff, and that didn't make sense to me, so I did a little more research, and I found this one. It was quite nice. But again, there's some massaging that has to happen, so the virtual deobfuscator does that and takes out some of these key words or massages it so that it fits or makes sense. So remember I was telling you about like the sections, and you can assemble that whole section. Well, that's great, but it's still more work. So what I did was in the virtual deobfuscator, it creates a final file called finalassembly_nasm.asm. And that is all the formatted, all the sections that fit within your range, all in one file. And so then you can just assemble that guy and throw it in Ollie. Which then leads me to my people optimizer. I don't even know if that's the right word anymore because it's not that. It's another code, deobfuscation type tool. So anyways, that one's called VD_peephole, and it's part of the source code package. You can download it, but it's pretty self-explanatory. You load up the binary, you run this guy, and it'll pull out all the code obfuscation and leave you with something good. So back to our blood alcohol example. Here's 5 instructions that were the original instructions that were protected. After removing the virtual machine, there were still 3,329, and just to represent these 5 instructions, and all that was code obfuscation. After running the peephole guy, I got it down to 359. The reality is I could probably get it even tighter, but I was running out of time, so it was good enough. But the point was I was able to reverse those 359 really quick and say it was equivalent to these instructions. So I'm having a good time at that point. So okay, as part of the project, I said, well, it's great handcrafted stuff, but I need to look at something real, you know, what's out there. So I grabbed the first one on offensive computing, which I think is now called open malware, called Win32 Clone AF. And as soon as I disassembled it, I saw a recognizable section called VMP0, and I ran it, of course, on the virtual deobfuscator. I've got a lot more information. I'm not going to spend a lot of time talking about what this malware did. If you're interested, go to the website and where the source code is and read all to your heart's content. Point is, though, within a couple hours, I was able to look at my run trace, filter out the virtual machine, and pull out these little nuggets that told me exactly what it was doing, which was the whole intent of the project. Remember, this is a tool not for an idiot, but for a reverse engineer that can run it and then get down and dirty without spending a lot of time fooling with the protection. Move on. Go. Okay. Oh, I skipped one. Let's see if I can't. Well, anyways, that's where you can get it from. And that's the disclaimer I got to put on there. And I can't get to the other slide, but really it was just future work. The idea was, you know, when I saw those code obfuscations, I thought, man, it'd be neat because, I mean, if I'm clustering all this kind of stuff, couldn't I not feed that into the clustering part of the algorithm and tweak it a bit? Because if you look at code obfuscation, machine code obfuscation, you'll find that it's repeated patterns all over the place, right? But I just kind of ran out of time, so it was like, Johnny on the spot, I just started writing code and start writing patterns to remove this stuff. So it's something worth thinking about. The other cool concept, I think, is by accident, but it makes sense, I ran UPX on this guy, you know, from a protection just to packing, and I found original entry point, which makes sense. Think about packers, right? What are they? Tight loops, repeated, you know, so what are we as reversers really interested in pulling in and analyzing malware is finding original entry point, right? So I don't think there'd be a whole lot of lifting here on this guy to make it work with lots of different packers. Like I said, I tried it on UPX and it was, of course, that's pretty easy, but it would be interesting to try like on WinLicense or something a little more juicy and pull out the original entry point. Or have it a little more automated so it just says, hey, here it is, instead of you know, digging through it. So that's it. Any questions? Yes.
Is it available immediately, or?
Yes. You should be able to go to the site and pull it down. It's got some, again, more documentation. I think it documented pretty well. At least that's what I was told. You know, yeah. So.
Well, it's tempting to go reapply the same technique to the obfuscations. Have we moved around for other obfuscation things which take instruction sequences in class for them to then do other things?
Well, I mentioned the other techniques that were used. They did not do that. I did, when I saw the code obfuscation, I went out to Woodman and pulled down some. I found a decent one, but it only removed like 1 or 2 code obfuscations from the machine code obfuscation perspective. It only removed 2, so I was like, I didn't have time. I was really running out of time, so I just wrote it myself. But I did look. I spent like a half a day. And of course, before I actually started doing this, you know, wrote up their proposal, I had to go read essentially what everybody else did, make sure that my idea wasn't, you know, ripping anybody off or anything along those lines. So, anything else? Yeah, sorry.
You highlighted the link, I can't read.
Oh yeah, how about that? That's great. Hang on. How's that? No good. Let me. Can't I? I could change like the or. What's at home? All right, help me out here. Here, just make it what? Do what?
One more than
This one? Yeah. All right. Oh, yeah. That's background?
Oh, no, it's only highlighted the
Weak. All right. Oh, God. I got it. Hold on. Shh. I was going to, but I think we got a winner here. Oh, God. All right, let's just do this. Yes. That's what I'm going to do. Where? Shh. How about this?
We should decide who you should do by vote.
There. You read that? All right. Excellent. I see another hand. I didn't bring it, no. Sorry. It's all up on GitHub, though. I mean, where you go to that thing, you pull it down, and yes.
How does it deal with conditional control flow? Because in a certain run trace, you're going to have diverging control flow. Do you do anything like try to reduce, two runs in parallel to get it more complete?
No, I didn't really do that. I wasn't what I was interested in is identifying the virtual machine. If you kind of dig through the virtual machine, you realize that they're doing like a RISC pipeline where they do a prefetch, fetch, access, decode, and execute. So what is happening is it's grabbing a byte at a time, and eventually then it executes it. But that virtual machine is doing a ton of heavy lifting, right? So at the end of the day, I didn't really care because the clusters found it and I removed it, and so what was left was what I was interested in, right? So. Anybody else? Yes.
So if I understand correctly, the final output right now is just an assembly listing. Is that correct?
Yes.
A lot of us in this community have gotten spoiled over the last few years with X-rays. And is there any plan or how hard would it be to take the current final output of your tool and I guess compile it into executable, and X-rays could then decompile for us so we can more efficiently analyze what we're looking at?
Yeah, I didn't really spend any time looking at it, I kind of ran out of time as the project wore on, but yeah, there were some ideas that I had that we could possibly do with that. I'm talking about dynamics, right?
Oh no, I'm just talking about making it into an executable again that can be loaded to IDA and then decompile.
Well, that was part of the, that was part of the repackaging phase, right? So I use NASM. So the idea is, with that, you put your range, you say, okay, well, clearly the clusters or that I'm interested is within this range, and the virtual machine is, 3,000 or 5,000 or whatever. So if you use that -S and put that range there, it will create a final file that's just those clusters. Then you feed that into NASM, and then you disassemble it and put it in IDAPRO.
Oh, so you can...
Yeah. Mm-hmm.
I misunderstand.
Sorry, yeah. Oh, no. What did I do? Hang on. Yeah, so the peephole, again, I don't like that name anymore, but it is what it is. The peephole optimizer was, it's a Python plugin for IDAPRO. Because I didn't want to, originally when I wrote up the project, I said, I'll do the peephole optimization first, then I'll repackage it, and you put it in IDAPRO and you look at it, it's all great. But then when I saw all those code obfuscations, I'm like, man, I don't want to write a whole disassembler, and so I'll use all the nice mnemonic handling and parsing that IDAPRO does. So that's kind of why I changed the ordering but yeah, here's the repackager, right? So I use NASM, and I do a little bit of massaging on the virtual deobfuscator because NASM doesn't like offset or whatever, like the immunity will spit out. So I did that to make it nice, and then, yeah, so.
Thanks.
Yeah.
So I wasn't clear. Is your code that's created in clusters, does it understand x86 assembly, or is it just?
No, it doesn't. So it could be ARM, it could be anything. So
I've seen these many strings in a row.
yes, sir. I mean, it's really based off kind of virtual address, and it does look at the instructions, but it's looking more from, so, polymorphic code or something along those lines, or, certain protections could put like encryption and then execute that, do some JIT and then clean out that memory and put some other code there. So it does look at the virtual address and look at the instruction, but not from a parsing of it's a string compare. It just says, does this instruction match this one later? Okay, great. Then it's the same instruction. Does that make sense? So yeah, it'd work on ARM, MIPS, or whatever architecture you wanted to apply it to. I don't know that they're doing that yet, but who knows? Anything else? All right, well, thank you. Working with the Air Force or working with some defense contractors and looking at malware and finding these types of protections. And one thing that is, if you play around with the protection, is the original binary is lost at that point. So like, if you're dealing with encryption or something along those lines and you have a stealthy way to probe memory and dump the memory, you can reverse engineer out the original binary into the semi-C code or whatever it was originally. But with this one, it's a lot tougher. Okay, so again, why do we care? Is because in looking at it, it's a really tough one. I mean, really tough. So if you do like from a static analysis perspective only, when you disassemble it, of course, if you got bytecode, the disassembler doesn't understand that bytecode, right? Especially if it's randomized each and every time.
Welcome to the next session. One reminder, as you're leaving the session, you can scan your badge at these pods that are at the doors in order to be able to provide us with some evaluation on the way out on Jason's presentation. So at that point, I will let Jason Raber give his presentation on virtual Deobfuscator.
Okay, so yes, as he said, my name is Jason Raber with Hex Effect, and today I want to go over an automation technique to remove virtual obfuscations from malware. So here's a quick overview. What the heck is this type of software protection? Why we even care? What is kind of the state of the art? What's been done? My solution? Some potential future. How I've done it in the past is essentially slogged, which that means start reverse engineering it, pull up dynamic static, find the bytecode. Once you find the bytecode, start reversing the VM so that you can create your own little disassembler, which is fairly fast, but still it could take a while depending on how complex the VM is itself and how complex the bytecode is. And then what I found out, a long time ago when I was looking at this stuff, is that the disassembler that I created and the work that I put into creating it and breaking at one particular protection, I was given another protection and it wasn't the same. And that's what I come back to, where it's jittered each and every time. So break once, break everywhere doesn't work. So I started thinking about, some sort of an automation technique would be nice. Work with this product and where to get the source code and any questions you have. So what is virtualization obfuscation? It's a type of software protection focused mainly on anti-reverse engineering. So there's lots of different protections out there, from encryption to anti-debugging to anti-tamper, but this one's focused just on anti-reverse engineering. And how it basically works is the virtual machine will create the bytecode from the original code, okay, and then with the current technologies out there, they'll actually randomize it. So each time there's a protection, it's a different virtual machine. So the opcode or the bytecode that's generated from the original code is going to change each time. So as you see, a lot of times they'll even pick a RISC type architecture. So I've looked at this in the past so it's hard to find that bytecode and you have to spend RE time to go find it. Then from there, if you want to take the dynamic and static, you can start looking at the run trace from it. Problem with that is you got a vast number of instructions, and it's hard to figure out where the virtual machine is versus the actual interpretation of those bytecode. In a case in point, on this project, one of the programs that I used was Themita, and I took one instruction and I turned up the VM completely with all its bells and whistles. And it went and generated a run trace for that one instruction of around 3 gig. So that's pretty hard to go through 3 gig and try to figure out what it's doing, right? So